Welcome to the lectures on modern digital communication techniques. So, just to summarize, till now we have covered modulations without memory, and then we have moved into modulations with memory. So, we have considered two kinds of modulations, one is without memory and one is with memory. And when we did with memory modulations, we have established that why would you call it with memory modulations. Just to quickly or briefly recapture what we have done, we started with FSK, where we said that you could select any one of the frequencies, and then we said you could do it by just selecting one of the oscillators, but that would cause an abrupt switch from one frequency to another, and this would give rise to a huge spectral side lobe. So, to reduce that, the other way you could do it is you could think of doing a frequency modulation using a digital waveform input to the frequency modulator. So, for that what we did is we took the data sequence and converted it into a PAM signal, and that PAM signal was used to frequency modulate the single oscillator. And then we found the expression had the typical expression of a frequency modulator, which is an integration in the frequency term. So, when we integrate over all possible previous symbols, that clearly means that you want to remember, you want to accumulate, and therefore, you want to remember the previous phases, and therefore, we have with memory. Then we did work around with the expression of the phase, and when we restructured it and tried to represent it in a new form without changing anything, just trying to put the terms in grouping them accordingly, what we found is that the expression of the phase looked like the expression of a continuous phase modulated signal, which is a more generic form. And there we had defined a few terms, and we had the modulation index and we had the accumulated memory term. In the CPM, we said that each symbol could have a different modulation index, whereas when we kept H is constant, we had a CPFSK signal. So, we continue on our discussion on the similar lines, and today what we have to discuss right now would be one of the special forms of CPFSK, which is the minimum shift keying. So, minimum shift keying, it is a special form of binary continuous phase frequency shift keying, where you have the modulation index H set equals to half. So, this is the baseline that we have with us, and we will proceed with this. And the phase, we have been always discussing the phase of the signal. Phase of the carrier is what we are interested in the interval t less than or equal to n plus 1 t and n t. So, that means t in this interval would be equal to phi of t, and all accumulation would be half pi k equals to minus infinity to infinity I k. These are the PAM signals, plus pi I n q of t minus n t. And we had defined all these terms in the earlier lecture, and we could write this as theta n, which is the accumulation of the memory. We have of course put h equals to half, that is why you do not see f h anywhere, and h is equal to 2 f d, if you would remember. So, that means 2 f d is equal to half, that means 2 f d t. So, f d t you could easily get it as 1 upon 4. So, that would work out to this expression, and then you have the remaining term as pi upon 2 I n t minus n t upon t, because you would remember q t was t by 2 t in this interval. So, this you could easily convert to t minus n t upon 2 t. So, this 2 t comes from q of t. So, once we have this, then you could write the carrier modulated or the modulated carrier, that is S of t, that is the band pass signal, which we have been always writing as S of t, as A cos 2 pi f c t plus, now we have this whole phase term, plus theta n plus half of pi I n t minus n t upon t, that is the expression directly from here, and of course, in the interval of t lying between n t to n plus 1 t. And this you could rewrite as A cos. So, we can collect the terms, we have an f c t term, we have I n t terms. So, you have a pi over here. So, we would rather take 2 pi and then f c I would take from here and the remaining term from this. So, since I have taken 2, so I should have 1 upon 4, t of course is here, pi of course has gone out, I n should remain. So, you could write I n and this t which is common you get over here. The next term that you would write is this particular term along with this, that means minus, because of this minus sign, half pi, t and t would cancel out, n I n plus, now you have the theta term left. So, you have theta and of course, valid for this interval, and in this case we would take I n to take the values of plus minus 1, because we are choosing between two levels, we are talking about binary CFFSK. So, moving into this expression, what we can see is that this term we could view it rather as there are two different carriers. So, we could write that f 1 is equal to f c plus. So, this I n, since it can take plus and minus values, you could take it as 1 by 4 t, and you could also take f 2 another value with a plus sign, f c plus 1 upon 4 t. So, if you look at it, it appears as if it can take two different values of frequency, f 1 and f 2. So, moving forward with this expression that we have just generated, what we could write is that we have two signals. We could write S I of t is equal to A cos 2 pi f I could take these values t plus, we have theta n from here, which we keep as theta n, plus we have 1 upon 2 n from here, pi, and we have minus 1 to the power of I minus 1 for I equals to 1 and I equals to 2. So, if I equals to 1, you have A cos 2 pi f 1 t, that means there is a minus over here, and n pi minus. So, when I equals to 1, you take the minus value and you have the minus value over here, this is also minus. When I equals to 2, you have 2 pi f 2 t, f 2 t is this value, which is because of I n to be plus. So, it is 2 minus 1. So, you could reverse it actually, you could say that f. So, this could become a minus, and hence this one would match with the expression that you have over here. So, moving further, what we have is we have these two frequency values and these two symbols that are with us, and then we could see an interesting feature of this is that the frequency separation So, the frequency separation that we have is delta f, which is equal to f 2 minus f 1, which you could easily calculate as f c plus 1 upon 4 t, which is f 2 minus f c minus 1 upon 4 t. So, f c and f c would cancel out, you would have 1 upon 4 t plus 1 upon 4 t, which is equal to 1 upon 2 t. So, this would remind you that this is the minimum separation in frequency required for orthogonality. Now, if you would make the separation smaller than this, you would not be able to make it orthogonal. So, what we see is that by choosing the value of h, which is half, and by choosing I n as plus and minus 1, you could generate a binary CPFSK signal, because we have used the same phase terms. Only in the phase terms we have replaced the values of h with half, and we have taken I n to be plus minus 1. Accordingly, we have got the expression that we just looked at, and by calculating or by working with the expressions, we could write it in terms of two different frequencies, as if there are two different signals, S 1 and S 2. So, this would remind us that we are supposed to select the waveform based on the input bit stream. That is the job of the modulator. So, we have to select two different waveforms, and these two waveforms that we have over here are with two different frequencies. One is f c plus 1 upon 4 t, the other is f c minus 1 upon 4 t, and of course, there is some memory term associated with that. And then when we look at the frequency separation, what we find, it is 1 upon 2 t. So, this is the minimum separation that we have, and therefore, this kind of a signal is also known as MSK signal, that is minimum shift keying signal. So, if we look at the expression that we have just had over here, and this is the S t and this is the S I of t that we have. So, we could also represent this particular signal that is with us in a simpler form. So, we are going to be interested and we are going to write that particular expression, and now what we are going to do is write it in a form which is representable as a 4 phase PSK. Now, that would make things easier. So, the low pass equivalent, that is what we are always interested in. V t, you could also write that expression that we had given there in a form which is sum of n equals to minus infinity to infinity I 2 n. We will explain what does this mean. G of t minus 2 n t minus j I 2 n plus 1 g of t minus 2 n t minus t, where g t is equal to sine of pi t upon 2 t for t in the interval 0 to t, and it is 0 otherwise. So, this is the typical expression, you could write it in this form. Now, we have I 2 n and I 2 n plus 1, and we have some g associated with that. So, would like to explain briefly what is the consequence or what is the meaning of writing it in this form. So, what we have with us in the previous expression, we had I n, if you would see, but now we have I 2 n and I 2 n plus 1. So, the reason of writing it in this particular way is that we are taking even sequence of symbols here and we are taking odd sequence of symbols over here. So, that means if this is my timeline and these are the values of n that you would get. So, let us say this is t oblique n that I put 0, 1, 2, 3, 4, 5 and so on, right. So, then we are going to get some value of I n because of, and we are having two different values. So, let us say that we have some values going like this, right. So, this would be I 0, this would be I 1, this would be I 2, I 3, I 4, I 5 and I 6. So, what it says is that if I had to send this signal, I would send this through selecting some waveform in this interval and selecting another waveform in this interval, selecting another waveform in this interval, and each interval I would select one of the SIs I is equal to 1 or 2. The other thing that we could think of doing is I could break it into two streams. In one stream I would put the evens and I would stretch it to double the duration. So, this is I 0, and then at I 2 I am going to get, at the n equals to 2 I am going to get I 2, I would stretch it for double the duration I 2. Then again at 2 I would get this, this I 0 I would go there, I would take I 2, again I am going to get I 4 and I am going to stretch it for this 2 duration, I 4 I am going to stretch it here, then I am going to get I 6 and I am going to stretch it there. So, this point is 1, 2, 3, 4, I 2, this is I 4, this is I 6. So, let me see if I have made a tiny mistake somewhere. Yes. So, this is 0, this is 1, this is 2, 3, there is some numbering offset that I got into right. So, this is the right numbering, and I would have another stream. So, this I would call the even sequence and this I would call the odd sequence. So, here what I am going to do is I 1 is starting at the index 1, I am going to take I 1 and it is stretching till this point. So, this is 1, 2, 3, 4, 5 and at 3 I am getting I 3. So, I choose I 3 and it continues for I 5, at I 5 at 5 I get I 5. So, here I get 5. So, here what you see is this is I 1, this is I 3, this is I 5, and I would modulate a cosine with this and I would modulate a sine with this, right. So, if I am going to do this, in that case each of the symbol duration would be becoming twice this period of t, this also is twice, but in a 2t interval I am sending 2 I values overall, one along the I channel, one along the Q channel. So, overall my bit rate has not been hampered between these two, and when I write it in this form, this modulates the cosine carrier, this modulates the sine carrier. So, that is what we have. So, if we would now look at what is g t minus 2 t, things would be becoming bit clearer now. So, if we would look at the expression of g t, g t was mentioned as sine of pi t upon 2 t for the interval t lying between 0 and 2 t. So, now we have the expression g t minus 2 n t and g t minus 2 n t minus t. So, we would like to look at those expressions. So, that means if we would say g of t minus 2 n t, so this is equal to this function for the time t minus 2 n t less than or equal to 2 t 0. So, you could get t lying between 2 n t and 2 n plus 1 into t. In this interval, this function is equal to this. The other form you could have done is you could have substituted t as t minus 2 n t over here, and you would know that it is valid for this interval, and this would again turn out to be the same thing. For instance, I could say t minus 2 n t. However, I would put t is equals to 2 n t plus tau, tau lying in the interval 2 t to 0. So, in that case, the moment I put over here 2 n t cancels out, I have pi of tau, and that is exactly what we have, and it is valid for this interval of time. Now, if we would see the other one, g of t minus 2 n t minus t, that is the expression that we have here for the I component, for the q component. So, here it was the I component cosine modulator, this was the sine modulator. So, that is what we have over here, and if we examine this term. So, for t minus 2 n t minus t in the interval, this what we get is t greater than this and t greater than 2 n plus 1 t plus t. So, in a similar way, if you would like to try putting this whole value over here, you would find this turning out to be sine pi of tau in the range of tau here. So, we could write this is also equal to sine pi t by 2 t for t in this interval, right, or in this case tau in the range of 0 to 2 t, right. So, these are the two things that we have, and using these two we could now see how would the waveform look like. So, if we would have time axis over here, and we could mark, let us say 0, this time I should draw it a little bit bigger. And so on. So, I need to draw quite a few timelines, so that it helps us. This is another timeline. This is another timeline. This is another timeline. So, what we would find is from this expression that we have is g of t is equal to sine pi t for this interval. So, that means if I would put n equals to 0, that means t from 0 to 2 t, right. So, I am going to get for 0 to 2 t sine pi t, right. If I put n equals to 1, so I will get 2 t to 3 2, this is 1 plus 1 to 4 t, that means from here to here I am going to get a sine, right. So, pi of small t upon capital 2 t. So, when small t equals to 2 t, you get sine of pi, which is 0 here again, and t equals to small t equals to capital T, you have sine of pi by 2, which is equal to 1, which is reflected here. The other time interval that we have depicted here. So, if we would put n equals to 0, then we are going to get t to 3 t. So, n equals to 0 means t to 2 multiplied by t, it is 2 t plus t, that is 3 t. So, that means from t to 3 t, and again in a similar fashion you would find when t equals to 2 t, in this expression it gets the maximum value. So, what we see is that the I phase or the in phase signal gets modulated by g t. So, now what we have is slightly different situation. We have the situation where g t is not equal to 1 upon 2 t. Earlier when we did FSK, we said g t is equal to 1 upon 2 t, but in this situation we are trying to write it in a different form, and we are seeing that this form of expression could have the meaning, that is what we are writing over here. So, here G t given by this term yields a picture which would be like, for the I term you are going to get a pulse shape which is sinusoidal in nature starting from 0 to t, 2t to 4t and so on, and the other one you are going to get from t. So, there is an offset of t and which is reflected by this term as well. And if you would combine the modulations, what we could get is that in one of the signals we could draw that you are, so this signal you are getting from here, so this is a sinusoid that you are getting. That means there is a carrier which gets modulated, right. There is a carrier that gets modulated. So, this is getting shaped over here in this form, it is getting shaped over in here in this form, and of course, it will get shaped in this form as well. And the second one is also going to modulate the carrier. So, what we are going to get over here is so, you can also clearly see that at 0 there is a cosine form and here there is a sine form. So, there is a cosinusoid and there is a sinusoid which gets modulated, and if you would use this together, it is some kind of a picture which is hand drawn, looks like this. If you generate the signal, it would appear better. So, if you would merge these two signals, the waveform that you would generate would be something typically of this order. So, what you are seeing is that in some portion there is a higher frequency component and in some portion there is a lower frequency component, right. So, as if you are getting two different frequencies. However, since you are doing an FM, there is a continuity of phase, and this has primarily been because you are using as if there are two different, they are using a pulse shape which is non-rectangular, and each of the non-rectangular pulse shape is modulating a carrier in the in phase and in the quadrature phase, and they are taking the input bit stream, dividing them into the in phase and quadrature phase. In order to maintain the bit rate, you are stretching the even bit stream to 2t duration, you are stretching the odd to 2t duration. So, that overall bit rate remains the same. However, you are modulating this with a cosine and you are modulating this with a sine, and together you would get a waveform which looks a bit complicated to draw by hand, but you could generate this if you are using some programming language and you would feed these functions into it, you could generate the modulated waveform for a MSK. So, in summary, we have got a waveform which selects between two frequencies, and we have seen the waveform how it looks like, where continuous phase condition has been maintained, and primarily there are two different frequencies which are used to indicate what is the original information bearing signal being 0 and 1, and it could also be represented as a 4 phase PSK, where you could write it in a form as if you are modulating a cosine and a sine with two different bit stream, but here tactically it has been handled in a way that the two different bit stream are as if at half the bit rate each, so that together they get back to the same bit rate. So, we conclude our discussion on MSK in this particular lecture here. We continue to see a few more similar things in the next lecture. Thank you.